Alright, chemistry, so this is my new setup that we'll be working with for the until the end of the year. There's also a ton of stuff going on around the house, so if you hear some other audio, that's because people are busy and we're all in this quarantine together, so that's what's going on. Alright, so at the top we have Kinetic-Molecular Theory, and basically we've gone through the ideal gas law in this chapter. So you'll remember the ideal gas law is PV equals nRT. All right, and in PV equals nRT, in the ideal gas law, we have pressure times the volume is equal to the number of moles times a constant times the temperature in Kelvin. So what this formula allows you to do is allows you to solve for unknown quantities as long as other things stay the same. So we can solve for the pressure. If we have the other three, we can solve for the amount of moles of a gas if we have its pressure, volume, and temperature. There's a lot of things we can do with PV equals nRT, or the ideal gas law. Now, this next section is about why this is correct. Why does the ideal gas law work? All right, and so that comes down to the kinetic molecular theory. And basically, what the kinetic molecular theory says is in a gas, you have a bunch of random particles moving around, and those random particles moving around are going to cause certain phenomena. So, for example, if the particles on average move faster in the same volume, so if they move faster in the same volume, that means this is going to stay the same. Temperature is going to increase because temperature determines how fast a molecule moves. If it moves very little, it has a cool temperature. If it moves really fast, it has a warmer temperature. All right, so if the volume stays the same, the number of moles stay the same, so the temperature goes up, and that means the pressure is going to go up. All right, and all these things are explained by kinetic molecular theory, or thinking of gases as tiny molecules moving around inside a container. Now, this graph here shows us the average or the number of molecules in a sample that have a certain velocity. So on the x or the y-axis here, we have the fraction of molecules. On the x-axis, we have the velocity. So we have several examples here of how a gas behaves at different temperatures. For example, at 100 degrees Kelvin. All right, that's pretty cool. And most of our molecules are going to be moving very slowly, less than 500 meters per second. All right, we don't have very many moving above 500, and we have a whole lot moving around in this region here. But as the temperature increases, as things get hotter and hotter, to where we get up to 1,000 Kelvin, all right, very hot temperature, 1 order of magnitude hotter, we get a wide variety of velocities. All right, there's a wide variety. And also, where have you seen this graph before? This looks very similar to the flatten the curve of COVID-19. So if we replace this with time and this as the number of infected people, we have a spike. That is one possible way to go. A lot of people getting very sick in a short amount of time. And we did social distancing and took measures to try and flatten the curve, or say we have the disease longer, people get infected longer, but the spike isn't as tall. Not as many people get it at once. It's more spread out over time. So you can think of the temperature of molecules, or the velocity of molecules in a gas, or the infection rate of this pandemic, but either way, it's going to be the same curve. You either have a spike or it mellows out into a relatively flat curve. So now, this formula up here, each of these curves is going to have an average velocity. So in each of these samples, whether the sample of gas is 100 degrees Kelvin or 1,000 degrees Kelvin, it's going to have an average speed that the gas molecules are moving at. And we're going to use this formula to calculate the average speed that the gas is moving at. So let's erase this. A little bit messy, but it'll work. Okay, so let's talk about this formula first. We have URMS. And so URMS stands for velocity root mean squared. And whenever you see root mean squared, you should just think average. What is the average velocity for these gas molecules? We also have square root of 3. All right, that's pretty basic, nothing exciting there. And then we have R. Now you might think that R is the same as the last equation, 0.08206, but that's actually not the case. This is a different constant, and this constant is 8.314 joules per mole Kelvin. All right, another variable we have is temperature, and lastly we have the molar mass. All right, so if we already have R, then to find the average velocity, the VRMS, all we need is the temperature and the molar mass. So let's go ahead and work that out. All right, calculate the root mean square velocity for nitrogen at 30 degrees Celsius. So we have 30 degrees Celsius, and we're looking at a molecule of nitrogen. All right, so looking at our formula, looking at what we're given, gotta move this back a little bit. We have a temperature, so that corresponds to our T, and then we have nitrogen, and that's gonna correspond to our molar mass. So the molar mass for nitrogen, let's find that out first. Now, you might be tempted to just look at your periodic table and say, oh, okay, it's 28 grams per mole. That's not what we want to use for this formula. For this formula, we're going to want to plug it in kilograms. All right, so we need the molar mass of nitrogen in kg, all right? And that's going to be our first step, or step 1. All right, I got to find a happy medium with this board here. All right. Step 1 is going to be molar mass of nitrogen in kilograms. So the way we do that, we take our original molar mass, 28 grams per 1 mole, and we set what we want on the top, kg, what we want to cancel. Now we want to cancel out the grams and put it in kilograms. So grams goes on the bottom. Now, how many grams are in a kilogram? 1,000. So we put that in, 1,000 kilograms, and then we get our molar mass for nitrogen as 0.028 kilograms per mole. All right, 0.028 kilograms per mole. Cool. Next thing we need to plug into the formula is this 30 degrees Celsius, but we don't use Celsius for equations in chemistry, we use Kelvin. That allows us to avoid any negative, nasty negatives that would mess up our equation. So, step number 2 is going to be to convert the degrees Celsius to degrees Kelvin. The way we do that is just to add 273 to whatever our Celsius temperature is, and that's going to give us 303 degrees Kelvin. All right, so now we have M, we have T, we can calculate the average velocity of a gas. So let's create some space. Right, I'm going to move these off to the side over here, 0.028 kilograms per mole. All right, and the temperature is 303 degrees Celsius, 303 degrees, or sorry, 303 degrees Kelvin. All right, so our formula, U RMS is equal to the square root of 3 times R. Now remember, this is a different R than we're used to. It's not 0.08, it's 8.314. Right, and then J per mole. And I'm not going to make you keep track of the units on this constant. Just know that this J's joules per mole Kelvin is the same as kilograms meters squared per second squared. All right, so this is actually the same as that, and this is what we need for our answer to come out to meters per second to get our velocity. But they're the same thing. Don't worry about them. Just get the number correct and put the right unit on at the end. All right, and then times the temperature. So we have our 303, and we'll go ahead and just use that. So, all right, so this 3 times 8.314. Since we have the space, we'll put in kg meter per second, or kg times meter squared per second squared times 303 Kelvin. We're going to divide that by the molar mass in kilograms per mole, which is 0.028 kg per mole. All right, then once we solve all that, go ahead and plug it into your calculator at home. And you should get a temperature of 519 meters per second. All right, 519 meters per second is the average speed of a molecule of nitrogen gas at 30 degrees Celsius. All right, so that's a pretty useful application of kinetic molecular theory. This one actually isn't a part of your homework, but know how to do it, be able to try it out. Go ahead and hop to the homework, only 2 questions, and we're going with more of a conceptual theme for this assignment. As always, let me know if you have any questions, and I will see you in the next video.